Hi everybody, Bob Sterner, and I'm here to talk to you right now about light and photosynthesis. Now what I want you to do is remember that photosynthesis in the cell can be broken into two basic pieces. We have photons illuminating the cell, and they first produce a response in something that we call the light reactions of photosynthesis, which you may remember is essentially a story about electricity flow through membranes, generating some chemical energy, and that chemical energy is then transferred into another place in the cell, another system of workings that we can call the dark reactions. And the dark reactions is where carbon dioxide is taken and turned into carbohydrate. So the light reactions is mostly about electricity flowing through membranes, whereas the dark reactions is mostly about chemistry, enzyme-governed chemical reactions. And the reason why that distinction is important will become clear in a minute. So what we're going to do now is talk about how the rate of reaction of photosynthesis, so the rate of photosynthesis varies with increasing irradiance or light level, starting from zero irradiance. And at zero irradiance, this is the light level in the environment, not the light level that the cell absorbs or anything like that. That's how bright the environment is. That's what we're plotting on the x-axis. At zero light, the rate of photosynthesis we can actually represent as a negative number. This is because the actual carbon balance of the cell is such that in the dark, the plant or the phytoplankton is not performing any photosynthesis at all, but it's still performing respiration. So that's kind of like a negative photosynthesis. A cell biologist wouldn't like to think about it that way, but we can. So at zero irradiance, we have more or less a negative rate of what we're calling here photosynthesis. And as we increase light from absolute darkness to some low level of light, what we find is that the rate of photosynthesis increases in very close to a linear fashion. So as we add light, we increase photosynthetic rate by some line that we'll now put in here. That line has slope alpha, and the point where it hits the x-axis, the x-intercept, we can refer to as C, the compensation depth, or compensation light level, sorry. The compensation light level is the amount of light in the environment needed for photosynthesis to make up for respiratory losses. So respiration equals photosynthesis, gross photosynthesis at the compensation point. The way I like to think about this first part, which I'm going to call zone 1 here now, the first part of this curve that we're drawing, this linear part, the way I like to think about that is that as we're adding light to the cell, that light's generating this electricity flowing through membranes, and that generates chemical energy, which goes into the dark reaction, which allows carbohydrates to be produced, and there's no saturation, there's no backup of it. The efficiency basically stays the same. So every photon coming in is generating the same amount of carbohydrate within this particular range. And that's kind of what you'd expect for a system governed by electrical flow or energy flow or electron flow. We could theoretically extend this linear relationship into higher light levels. But what we find is that as we add light, at some point we fall off of this line and the curve basically starts to bend down. We get a reduced amount of photosynthesis for every added new level of light. This is kind of a drop off in efficiency here in this range. the maximum rate of photosynthesis the cell can achieve, we can call Pmax. So that's maximal photosynthesis. I'll just say photomax here. And we can talk about the intercept between the theoretical extended line and Pmax. So we can project that down to the x-axis. That gives us an amount of light that we can call IK, is usually the term that's used. And IK can be thought of as the saturation level of light. We're going to call this zone 2 that we just talked about. Zone 2 is the zone of saturation. And the way I like to think about that is, as we increase light hitting the cell, now light's coming in, but effectively that energy starts to back up, because this chemical system here, this enzyme-driven chemical system, can only respond at some maximal level. It's a little bit like enzyme kinetics. You may have studied that, where the rate of a reaction V is a function of substrate concentration S, shows something like a hyperbolic relationship that maximizes at some level. Some people refer to this as the Michaelis-Menten relationship. And so in this zone 2, the zone of saturation, this part of photosynthesis takes off, or rather takes over, and we have more like enzyme kinetics than pure electricity flow through membranes. There's another thing that happens as we increase light even further, and this is a kind of a tricky part of using photosynthesis relationships in the real world, in the field, because if you take phytoplankton cells, or this is true for higher plants too, and expose them to very high irradiance for a prolonged period of time, minutes, certainly hours, then instead of being at Pmax, we start to get reduced photosynthesis out of it. So as we increase light further beyond zone 2, the rate of photosynthesis actually decreases and drops off. This is obviously a very big drop in efficiency because we're adding more light but getting less photosynthesis out of it. This zone 3 is the zone of inhibition. There's a general term used here, photoinhibition. That represents this drop off here that we see in zone 3. Photoinhibition is a dynamic thing. It is an expression of the fact that photosynthesis decreases at high irradiance beyond some level. Mechanistically, photoinhibition can occur from a variety of things. We're not going to care so much about that now, but for example, the cell photosynthetic machinery can actually start to fall apart or break at very high light. This can happen from ultraviolet light. It can also happen from photosynthetically active radiation, but especially ultraviolet light. So the light actually becomes detrimental to photosynthesis because instead of fueling a beneficial reaction of creating carbohydrate from CO2, it starts to do damage. There's a couple of other things that can be going on to cause photoinhibition, but again, that's kind of a more advanced topic and not really necessary to understand the functioning of lakes. So that's what I have for you today. Basically, photosynthesis irradiance curves, PI curves, can be broken into 3 regions. Zones 1, 2, and 3 is labeled here. A region of constant efficiency. With increasing light, we get increasing photosynthesis at a predictable linear way. And a second zone, the zone of light saturation, where chemical reactions start to saturate and we reach a maximum photosynthesis rate of Pmax. And then zone 3, the zone of photoinhibition. That's it for now. Talk to you later. Bye.